So today's video is going to continue to look at locations and distribution and how we can use them, but we're going to be focusing specifically on what we call normal distributions and how we can use those to calculate values. So first off, let's talk about what is called a density curve. And so a density curve is going to give us an overall shape or an overall pattern of the data. So because it's an overall pattern of the data, things like outliers would not necessarily be included because it's just kind of giving us a broad overall pattern. You can see how one has been created here on the left from the histogram. Basically just kind of drawing a smooth curve over the peaks of the histogram is how we can create that density curve. Some other characteristics of density curve is that the area under the curve is always equal to 1. That's going to be important later as we are going to be able to use the area under the curve. If you look at the density curves that are made in this bottom diagram here, you can see how they've shaded in this area here under the curve. We can use the fact that we know that the area under the curve is equal to 1. We can use that information and we can use the area here to help us calculate percentage or probability. Okay, so we do need to remember that the area under the curve is always going to be equal to 1. In addition, density curves are always going to be located on or above the x-axis. So these would be kind of our major characteristics of a density curve. Overall pattern of the data that's not going to include our outliers, area under the curve being equal to 1, and the curve is going to be located on or above the x-axis, meaning it's never going to look like you're never going to see it dip under the x-axis or anything like that. Okay, so all of these would be examples of density curves. And so let's kind of look at where mean and median would come into play with these density curves. We've talked about this a little bit before. So if the density curve is symmetric, like this one here on the right, the median and the mean are going to be located in the same place, right? If we're looking at the median, that's going to be where our areas are going to be evenly divided on each side of the point. So that in a symmetric curve, that would be in the middle there. In a skewed distribution, the median is not going to be at the top of the peak, but it's also going to be located closer to the peak than the mean would be. Because remember, median is resistant to those outliers and such. So our mean is going to be what you can think of as your balance point. So this would be where the areas are going to balance. And so what that will look like in a skewed right? So here we've got a skewed right distribution here. I'm going to find my mean where I can balance this distribution. So too close to the tail, it tips left. It's going to tip over this way. Too close to the peak, it's going to tip over that way. So I find my balance point here, which is going to be my mean, which again will be a little bit further down the tail from my median. A specific type of density curve is called a normal curve. You'll notice normal is capitalized. Okay, it's always written capitalized to realize that this isn't necessarily normal, as in like this is the norm and all of our data looks like this, and any data that doesn't look like this is weird or abnormal. It's normal just in the sense that that's how the distribution is described. So it is capitalized to realize that this is just referring to a special distribution, not actually what is quote unquote normal. So both of these are examples of normal curves. So some things that you should hopefully see in common with these is that normal curves always have one peak. They are going to be symmetrical. Okay, and the mean is going to be at the center. And you'll notice our notation that we're using for mean here is this mu symbol. Notation is important with this. Mean is at the center or the peak. Let's go with at the peak. And the spread is going to be controlled by the standard deviation. Notice your standard deviation notation is your sigma. And so your standard deviation is going to control the spread. So for example, this one on the right here has a smaller standard deviation, and this one on the left here has a greater standard deviation. That's why it's more spread out. Commonly, these are called a bell curve. We will never refer to it as a bell curve. We will refer to it as a normal distribution. When you are labeling these curves, so when you draw them, you always need to label them, and you're going to label them with a capital N, and then you'll put your mean value, a comma, and your standard deviation value. And you'll put the actual values in there, and you'll see that as we go through and do example problems and we draw and label these. But you have to label them to ensure that you get credit for realizing that it's supposed to be normal and you know the mean and the standard deviation of the curve. So when we're using a normal curve, we can apply a rule that is sometimes called the empirical rule. And some of you may be familiar with this. The empirical rule, or the 68, 95, 99.7 rule, is going to state that 68% of our data points fall within one standard deviation below and above the mean. So basically what that looks like is that 68% of your data points are going to be, if our mean is here, are going to fall plus and minus one standard deviation. So in that window, that's the light green that we're seeing here. So that's going to cover 68% of our data points. 95% of our data points, notice it's 68, 95, 99.7, 95% of our data points are going to be plus or minus 2 standard deviations. So they're going to fall in this chunk of our curve right here. So when we say 95% of our data points and 68% of our data points, remember the area under a density curve is always equal to 1 or 100%. So basically what this is saying is that this area right here, from here to here, filling this whole big chunk of our curve here, that is 95% of the area under the curve. So 95% of the data points fall in that range. When you go all the way out to 3 standard deviations, you should be covering 99.7% of your data points at that level. Okay. We've already calculated outliers one way with median and our IQR rule. Okay. This is another way you can look for outliers using mean. Anything that is above 2 standard deviations or below 2 standard deviations from the mean, you can look at that a little closer as a potential outlier. So let's look at how we could apply this rule to solving, for instance, a problem like this, with this distribution of these vocabulary scores for 7th graders in Gary, Indiana. Okay, it tells you here that it is normal, so that's important. Okay, you'll notice they've got their capital in there, and then it just says 6.84 and 1.55. Well, based off of our notation that we used before, remember that's going to represent our mean and our standard deviation. So we're going to sketch this curve out. Okay. You'll get better at it the more you do it. So we're going to have 6.84 is going to be here. I'm going to label my curve so they know which curve I'm referring to, because every normal curve I draw is going to look the same. Okay. And so if I don't label it, they don't know which actual distribution of data that I'm referring to. So when I add 1.55 to 6.84, I get 8.39. And my second standard deviation, when I'm going to add another 1.55 to that, and I'm going to end up at 9.94. And then for my third standard deviation, I'm going to add another 1.55 to that and end up with 11.49. So a couple of things about drawing your curves. So when you're drawing your curves, we mark the first standard deviation where our curve starts to kind of dip down. And we mark the second one where it starts to kind of level back out. Same with the third when it's really starting to level out some more. Those actually maybe should be spread out just a hair more. So when we're figuring out these numbers here at the bottom for those of you that aren't as comfortable with this, right? This is my mean plus 1 standard deviation. This is my mean plus 2 standard deviations. This is my mean plus 3 standard deviations. And then I do the same in the opposite direction. I make my marks where my curve starts to dip down, okay, where it starts to level out, and then again where it starts to level out again. Now when I'm going down, this time it's going to be, this is my mean minus 1 standard deviation, my mean minus 2 standard deviations, and finally my mean minus 3 standard deviations. So in looking at those values, my 6.84 minus 1 standard deviation is going to give me 5.29. Minus 2 standard deviations, 3.74. And minus 3 standard deviations, 2.19. So to use this curve to solve the problem here and show my work, that means I'm going to sketch the curve. That counts as showing my work. And I'm going to shade the area of the curve that I'm looking for. So it's asking me the percent of ITBS vocabulary scores that are less than 3.74. Well, conveniently, 3.74 is right here. And it wants less than. So I'm going to shade that area. This is going to be really important and a very good habit to get into. Okay? I know a lot of you are going to think, oh, I don't need to do that. That's no big deal. First of all, every point you could possibly get for showing your work with a normal distribution situation, you're pretty much going to cover it right here by drawing this curve and shading it. And every single person, no matter how awesome they are, including myself, I draw the curves all the time. You're going to screw up which direction you need to go at some point in time, right? But if you draw it, you see it, you know exactly which direction you need to go. This becomes important when you are not using this empirical rule and you're using your calculator or table A to do these calculations. So it wants to know what percentage is basically less than 2 standard deviations away. Well, if I remember correctly, right, this area of my curve right here is 95% of my curve between the 2 plus and minus 2 standard deviations. Well, I know my area under the curve is 100%, right? So 100 minus 95 leaves me 5% of my curve left over. But keep in mind that 5% is split into the two sides. It's split into this tail and this tail. So what I really have is 2.5% on one side and 2.5% on the other side. So my actual percent that got less than 3.74, that is going to be equivalent to 2.5%. Okay, so the next question there is asking us what percentage of scores are between 5.29 and 9.94. So I'm right here, right? I'm minus 1 standard deviation up to plus 2 standard deviations. So I want that window right there between those two values. Well, I know that this right here in the middle is 68%. Okay, and what I need to figure out is what this little bit right here is. Well, again, from 2 to 2, from here to here, is 95, right? That's my 95%. Well, I've already used 68% of it. So 95 minus 68 is going to give me 27. So again, split between these two wedges here is 27%. Well, I have to split it between the two. So what that means is approximately 13.5% fall right there. So now I just need to add these two together. And I end up with approximately 81.5%, approximately 82% of the scores are between 5.29 and 9.94. Okay, so pause, take a second, try to do these examples by yourself, and then come check your work. Okay, so for number 1, hopefully your curve ends up looking like this. Remember, make sure that you labeled it. Again, remembering to put the mean and the standard deviation with a capital N. Remember, always a capital N. And then you went both up and down with your standard deviations. Question 2 asked which heights were greater than 67 inches. So again, we draw like I did with the blue and we shade it in, and that's the areas we're looking for. And there's a couple of ways that you can approach this. If you remember from our previous problems that this tail is 2.5% and this little chunk was 13.5%, well, you can just add those together to get your 16. If you didn't remember that, okay, again, from 2 standard deviations to 2 standard deviations, that's my 95%, right? So again, 100 minus 95 leaves me with 5% of my curve left over. But remember, that's split between 2 tails, right? It's split between this end and this end. So 5 divided by 2 is what gives me the 2.5% of that little tail. Okay. Also keeping in mind here, remember how we got the 13.5%, right? Again, my up to 2 standard deviations is my 95%. I already used 68% of it. So the remainder there of that 27, right? I take that remainder of 27%, divide it by 2, and split it amongst the 2 tails. And so now I can add the 13.5 and the 2.5 together. The third question there, percent of young women that have heights between 62 and 72 inches. So this time we're going from here all the way over. So basically what you can think about this as, and remember to be making these kind of adjustments and stuff, basically you have this left over, which is the opposite of what you just solved at your 16%. Right? You just have the 16% on the left side left over. So I can just 100 minus 16 gives me approximately 84% of them are between 62 and 72 inches. So let's look at some sources we can use when things don't fit this nice, neat empirical rule, which is going to happen most of the time. You can use what's called Table A, which is part of your formula chart. So you may want to grab your formula chart as you're moving through these next couple of problems. I will also try to talk you through how to do some of this on your calculator, but we'll definitely show you how to use your calculator to do this when we move into the class, when I see you in the classroom. You will not be required to use Table A. You will be able to choose between the two when you're taking quizzes, tests, and your AP test in the spring. So looking at Table A, which is called the standard normal table. So our standard normal table basically is a table of a whole bunch of areas under the curve at particular z-scores. Okay, so what we have here down below is what's called a standardized curve. So this is our standard normal curve. So based off of a data set that has a normal distribution that we then took the z-scores of all of those pieces of data from that normal, from that same normal distribution. So the shape of our curve did not change. It still has that normal distribution shape, but it brings our mean, right? This curve would be labeled as a mean of 0, standard deviation of 1. So we have to calculate those z-scores to be able to use our Table A. When you're doing it in your calculator, you don't necessarily have to calculate the z-scores. The only issue I have with the calculator is it sometimes makes people forget that z-scores are a thing, and sometimes you need them in other places. So when you use the table is going to give you the area to the left of whatever z-score you're talking about. So what we have here is like a little zoomed in piece of the table. And so you'll see the z is going to be in the upper left-hand corner. And you'll notice it's got the tenths place for the z-score, as well as the ones place, because you'll see, I think your Table A might go all the way up to 4. And then the hundredths place will go across the top. So for example, if I have this z-score right here in this curve that's shaded green here, I have a z-score of 0.81. So I find 0.8 here, 0.01 here. So come together, right? And that is 0.81. And where those two meet, that's my area. So what that means is this area shaded in green here is 0.7910. And that's how I'm going to use Table A. I'm going to use my z-score that I calculated to then go find an area under the curve. So what if I need to find an area that's between, like we did on that last set of problems when we were using that 68, 95, 99.7 rule? Okay, I'm going to use this picture to do it because I think it's probably clearer than what I would write there. So it wants the proportions that are between negative 1.25 and 0.8. So how you can think about that, right, is negative 1.25 and z-score and z right there. So that's what that would look like if you wrote that out. So on these curves that should be labeled 0, 1, and 0, 1, and 0, 1. So on these curves, there's kind of a couple of ways you can do this. Okay, this is a time where I think your calculator is going to be a little bit easier to use. Remember, my table shows me what's to the left. So we already used our table before to find that this area to the left of z-score 0.81 is 0.7910. And then if I used my table A again, it has negative and positive values on it. I can find the area to the left of negative 1.25, which is 0.1056. So it's this little tail right here. Again, I want the area between. So finding that little tail here, finding the area there, if I subtract that off of the z-score, off of the area that I found from the z-score of 0.81, I can get the area between. So when I subtract those two, I get 0.6854. Another way that you could approach this, I'll do that in green, is you could find what this area is here, right? And so to find the area to the right of 0.81, I would do 1 minus 0.7910, which will give me, let's see, 0.2090. So now what I have is I know that this is 0.2090. I know this side, because I can find it to the left easily, is 0.1056. So I could do an overall 1 minus the two of those added together, which will still give me the same of 0.6854. It doesn't really matter how you do it. Okay, you're going to get the same answer either way. So what about working backwards? What if you were given an area and you wanted to find the z-score? Like in this example here, how you were given an area of 0.9 and it wants to know what z-score that falls at. Okay, so again, you can use table A and just use table A to work backwards. And you can also use your calculator, which I think is a little bit more specific. So basically, you just find the area closest to 0.9. You'll notice when we're looking at our sample here from table A, there is not an exact 0.9, but this 0.8997 is actually the closest. It's closer than 0.9015. So I'm going to take that and I'm going to just work my way out. Remember, that's my ones and tens place to the left, and to the top is my hundredths place. So what that would give me when I put those together is a z-score of 1.28. In your calculator, this is going to be a calculation called inverse norm. And again, I find inverse norm to be much easier than trying to search the whole table, because the table's kind of big. You're searching this whole table for a probability value. And that isn't usually even there. And then now you're just trying to find the one that's closest. Okay, so take a minute, try to use table A to solve these. Again, I told you you're going to need your formula chart. You'll find table A near the back of your formula chart. Okay, so for the first one, you are looking for the probability of the z-score less than 1.39. So we're looking for this area here. Remember, our table shows us to the left, so I can pull that probability straight from my table. Remember, going down the left-hand side of the column, I would look for the 1.3, and then I would go find the 0.09, which is at the very, very end, and where those two intersect is at 0.9177. So that would be my probability, or my area under the curve there, my percent of this happening, 91.77%. The second one is looking for greater than negative 2.15. So this time I'm going to the left. Okay, so I'm going to the right. So I make sure I shaded that, but I'm going to the right. So this time when I look up the area, remember my table is going to give me this area here. So I need to do a 1 minus calculation here. So when I use my table, I find, again, when I go down the left, I find the negative 2.1, and across the top, the 0.05, they meet at 0.0158, and I subtract that from 1, which gives me 0.9842. For the third one there, I need to make sure that I'm realizing I'm going to the left. So I need to go ahead and find my probability of 1.81 using my table, which is 0.9649. And then I need to go ahead and subtract this area here because, again, my table gives me what's to the left. So I go to my table. I find my negative 0.56. So make sure you're looking in the negative section. Make sure you're looking at 0.56. And that value is going to be 0.2877. And when I subtract those, I'm going to get 0.6772. Okay, so make sure you have those and you've checked your work because I'm going to erase them to show you the answers for 4 and 5. Okay, so for 4 and 5, you are going the opposite direction. So it gave you the area in number 4, the 20th percentile. So that's 0.2, right, a percent of my curve. So basically, I'm going to go back to my table. I'm going to look in, right, I have my z-scores on the sides. I'm going to look in the middle, and I'm going to find the closest value I can to 0.2. And when I find that value, I'm going to work my way out to the edges of my table to determine my z-score, which in this case is going to be negative. The negative is very important, 0.84. The second one asks us to do all observations greater than z. But again, remember my table shows me what's to the left. So what I need to do is I need to determine this area here, which is 1 minus 0.45 or 0.55. Now, if I look for 0.55 in my table, I get a z-score of approximately 0.13. It's between 0.12 and 0.13. If you do it on your calculator, you get like 0.1256. Okay, so let's talk about what this looks like on your calculator. So even if I'm doing the work on my calculator, I am still drawing the curve because that's one of the places that I'm going to get credit, and I'm sure I'm going the right direction, that kind of thing. So I'm going to label my curve with my mean, my standard deviation. I'm going to go ahead and calculate out what all these values should be and go ahead and finish up my curve. Okay, so that's the picture of what I'm trying to find, right? That's the picture of what I'm trying to do. And so if I was using my table, I would have to do 1 minus my table A value. So let's walk through what this looks like on your calculator. So on your calculator, hopefully you have it in your hand. On your calculator, you are going to go to that distribution menu. So that second, let me pull mine up real quick. You're going to push second vars. Right above vars, it should say the abbreviation there for distribution. So you want second vars to get that. When you open up that menu, you'll see a variety of distributions. Number 1 will say normal PDF. Number 2 will say normal CDF. And number 3 will say inverse norm. The ones we are concerned about at this point in time are numbers 2 and number 3. We will not use normal PDF. So make sure you don't push that. You will not use normal CDF, normal PDF. So when you're writing your work for this, you're going to go ahead and arrow down to the number 2, to the normal CDF, and you'll notice it pulls up a lower. So our lower here is going to be 290. So you'll go ahead and type in 290 where it says lower. Our upper is going to be a really big number, okay? Because essentially these curves go to infinity. So your upper is going to be a really big number. It doesn't matter what it is. I just type in 1 and a whole bunch of zeros following it. And then you'll see a place for the mean. So you need to make sure it fits your curve, right? Your curve is, the mean is 304. So make sure you alter that so that it says 304. And then make sure the standard deviation right below it also fits your curve at an 8. And then you'll arrow down to paste and you will hit enter on paste. So what you should have in your calculator, it should pop up. You might not be able to see the first part of the words, but it'll say normal CDF, and then I'll have a parentheses. And this is the work that you need to show. You need to write the word lower. Your calculator doesn't write it. It just shows 290. You need to write upper, and you can go ahead and infinity that out. You need to write that you use the mean, and you need to make sure your notation is appropriate. You need to write standard deviation of 8, and you need to close your parentheses. That counts as enough work. That is fine. So when you hit enter on your calculator, it will give you this probability of 0.9599, which is the appropriate probability. You do not need to subtract from 1 because you set your lower boundary at 290 and your upper boundary at infinity. So it calculated that area to the right for you. And again, that's the work you would need to show in your, you need to write down on the piece of paper. So you would need this drawing here, and you would need this information here, and then you would need to interpret that in context. 95.99% of Tiger's drives travel at least 290 yards. Okay, so the same thing would apply for here as well. I would draw my same curve that I had before. So I draw my same curve, I set my boundaries, I go into my calculator, second vars, so I get that distribution. Normal CDF, notice that I wrote what I was using. My lower this time changes to 305. And now my boundary is not infinity. My upper boundary is not infinity because I did not go to infinity, right? I didn't just say how much was bigger. I have an upper boundary of 325. So I need to change my upper boundary to 325. My mean is still 304. My standard deviation is still 8. When I hit enter on the paste, again, my calculator doesn't show these words. So you cannot just copy what's in your calculator. You have to show that you know what the 305 is, the 325, the 304, and the 8. So you have to write lower, upper, mean, standard deviation. But then when you hit enter, you'll be given that probability of 0.4459. So what you know then is that 44.59% of Tiger's drives travel between 305 and 325 yards. Okay, so for this problem, it's talking about cholesterol in 14-year-old boys. It told me that it was normally distributed, and it gave me my mean and my standard deviation. So the first thing I'm always going to do is I'm going to draw that curve, and I'm going to label it. And now my question is asking me the first quartile of the distribution of blood cholesterol. So basically what I need to remember is that my first quartile is going to land at 25%. So I need to find out where I've got an area here of 0.25, and I need to know what this value is. So again, I'm in my calculator using second vars, getting that distribution menu again. And this time I'm going to go to the inverse norm button, number 3. So you'll notice this time it asks me for different information. It asks for the area. So I need to put that in decimal form because remember the area is always equal to 1. So these proportions here, these probabilities are always a decimal. So my decimal here, I'm going to put in 0.25. And then I'm going to put my mean of 304 because I'm still using the same. Oh, I'm sorry, not 304. We're not on the Tiger problems anymore. 170. And my standard deviation of 30. And when I hit paste, right, it's going to bring up the inverse norm. And again, my calculator is going to show me those numbers. To show my work, I need to write what those numbers mean. So I need to write area 0.25, mean using my appropriate notation, standard deviation of 30. You notice we're not using X bar here, and we're not using S of X for standard deviation. We are using mu and sigma. Notation is going to be really, really important for you. And then when you hit enter, you should get a value of 149.7653. So what that means is that the first quartile of blood cholesterol levels in 14-year-old boys, in this sample of 14-year-old boys, lands at 147.7653 milligrams per deciliter, because we like our units. Okay, we'll be doing tons and tons and tons of practice problems with these. Okay, and this wraps up the end of Unit 1.